Ok, bienvenidos. Vamos a tener ahora la primera parte del curso de Julian Bautista. Nos va a hablar sobre Lya I. Él hizo su tesis en este tema, que es una tesis muy completa que hemos estado utilizando justamente para aprender de Lya I. Y es un gran placer tenerlo aquí. Entonces, va a constar de 3 partes. Esta es la primera y
Bueno, gracias. Primeramente, un gusto de haber recibido la invitación para venir a hablar con ustedes de esto. Y bueno, como yo nunca hablé de física en español, entonces yo voy a hacer la clase en inglés. Pero voy a tratar de hacerlo despacio. No sé si quieren hacer preguntas en español también, pueden hacer como quieran. ¿Okay? Entonces, la primera charla va a ser productiva, va a ser más a los que les gustan las ecuaciones, va a ser sin ecuaciones. y bueno, vamos a empezar bien despacio, viajando un poco por el universo, mostrando fotos de estrellitas. Okay, I'm going to switch to English now. And then you can stop me anytime you want. And the first lecture actually is not going to have any lemon of forest. Okay, it will be mostly introduction to BAO, Baryon Stations. I want to know here, raise your hand if you never heard about acoustic oscillations. Never. Okay, it's about a third. The class. Okay, that's good. I'm gonna try to introduce it without equations. No, just a bit. Okay, as this is the plan for the 3 lectures. The first one is the biggest one's 2 hours, or maybe less than 2 hours, about introduction to cosmology and BAO. The second one will be about Lyamanov forests, mostly just Lyamanov forests. And then the third one will be about the most recent measurements. What's the state-of-art cosmological constraints from these measurements. And I am part of this survey called EPOS, so that's why I'm talking mostly about those results. For this lecture, this is my plan. First, we start with a cosmic trip. So sit back, relax, enjoy. And then we talk about distances in cosmology. I like to talk about this. Start talking about distances in general. It's a nice way to start a topic before talking about BAO. The third topic is about expansion of the universe and how it's related to dark energy. And then BAO to measure distances. Okay. So first, cosmic trip. This is a picture of the sky. Can I turn off the light? You see better. So just a picture of the night sky. As you would see far from the city, you see, what do you see here? You see planets. You can see clearly Saturn, Venus, Mercury, Jupiter on the sky. You can see other stars. All those dots here are stars from our own galaxy. You can see our own galaxy here, all those millions and millions of stars that form our Milky Way. You can see it on the sky as well if you're lucky and it's dark enough, you can see it. And the galactic center should be there. It's a beautiful thing to start the trip. So let's talk about distances then. What do you see here? I'm gonna put this in this plot here. So 0 is here. This is from XKCD. I don't know if you know this. They make cartoons about science and philosophy. It's very interesting. So they did this one about distances and what's inside the universe. And this is in a log scale. So the sizes are, of course, not to scale, but the heights above the Earth's surface are accurate on a log scale. Okay. So if you start from here, from the tree, above this, if you go twice as big, it's actually 10 times higher, or something like that. One interesting fact for the French people in the room, The Eiffel Tower, it's actually linear in log space. If you take a photo and put it in log space, if you're very bored, it was gonna look in log space. It's gonna look like two sticks linear. Okay, so you have the tallest building on Earth, how helicopters can fly, airlines here, balloons, and then the official edge of space, and then we go up. The International Space Station is flying 100 kilometers above Earth's surface. Have a lot of space junk, apparently, trash. You see the movie Gravity, maybe, so it's very dangerous. GPS satellites are a bit above, and then quite far away you have the moon, and then satellites are going to the moon, etc. The sun is just here, and the other planets in this scale. So I'm gonna put some distances here, just for you to give an idea. The moon is 1 light second away from us. That means the light takes 1 second to reach us, okay? And that defines the distance, 1 light second. When I talk to people about astronomy in general, about this distances in astronomy in general, I always talk about light seconds, minute seconds, because the sun is amazingly 8 minutes, light minutes away from us, right? And if you look at the Voyager 1, is the farthest satellite from us. The object, man-made object, it's the farthest from us. It's outside the solar system right now, and it's at 16 light hours from us. It's very hard to communicate with that. It takes a lot of time. You need a lot of patience. And you have the limits of the solar system with this thing called Oort cloud. Maybe it's there, maybe it's not. It's not proven yet to be observed, I think. And then you have 1 light year already here. Okay, and then nothing. This is amazing. There's nothing between this and the closest star from us, Alpha Centauri, which is 4 light years from us. They discovered recently that they have planets here in this solar system. And so imagine if you want to travel there to another different local solar system, it will take at least 4 years to get there. You can travel even very fast. So it's amazing how big it is, everything. So you have other stuff here. You have Orion Nebula. It's here. I'm sure you know this constellation with the 3 stars. In Spanish, they call this Tres Marias, I think. And they are, so if you zoom in, you have the Horse Head Nebula. I'm sure you know about this one. It's a beautiful picture from the Hubble Space Telescope, which is already 1,500 light years from us. Okay, and then we keep going. This is cosmology, so we need to go very far. So our center of the galaxy is here, and you can see it here too. It's 30,000 light years from us. That gives you the scale about the size of our galaxy. It's about 50,000 light years. Andromeda, if you look at this, it's very faint in the sky, but imagine you can take a long exposure picture. And this is how Andromeda would look like in your sky compared to the moon. It's about 5 times the moon in size, pretty big. But it is already at 2 million light years. To give an idea, our galaxy is about 100,000 kilometers across. If you pick 20 of them, you reach Andromeda. Yeah, Andromeda is here, it's in scale, and then other galaxies have 1 billion light years, and then the Hubble Deep Field objects. So this is a movie just showing what is the Hubble Extreme Deep Field. It's a picture taken from Hubble. So it's zooming in to the region of space, a very tiny region of space where Hubble took this picture and took a long exposure of this part of the universe. And people maybe thought at the time that there was nothing there, And if you expose long enough, you see all those galaxies. They are very, very close to the beginning of the universe. Okay, so 23 days exposing this for this picture. And the field is about this size compared to the moon. Very nice. So I have galaxies from redshifts of 6, 7 here. The oldest galaxies were detected when they took this picture. So it's around 13 billions of history here. You can see on this picture here. You have closest galaxies and farthest galaxies, etc. And what is behind all this? All those galaxies. If you take all the galaxies and you have the limits of observability with light, it's the cosmic microwave background. I'm sure you've all seen this picture before in the news, or I don't know, you worked with it. So this is from the Planck satellites that took this picture in microwaves, and of course you have a lot of emission from our own galaxy that here's in the middle. But if you're smart enough and you can clean this map, what you obtain is this one, which is behind, which shows the cosmic microwave background this time, and this is light from when the universe was only very young, so 300,000 years old. So this corresponds to a redshift of 1,000, and this corresponds to, it's actually a map of the universe, density fluctuations that correspond here to temperature fluctuations of this light. And those fluctuations are about of 10 to the minus 5, 1 in 100,000, 1 part in 100,000. So they're tiny, tiny, and it's really a picture of the beginning of the times of our universe. And so, yeah, looking at all those things, we could make this picture of what we think is the history of our universe. We are here today, this is time. We're here, we have the galaxies I've shown and planets, and then the galaxies forming, and the CMB is here. This is again log scale, we have the times here. This is, we think, happened in the Big Bang, and you have this period of inflation, very fast inflation, and then you have this hot plasma, and then the CMB here. Okay, so all those distances, they're very hard to measure. If you think about them, how do you measure distance from a galaxies or this kind of things? So the first very basic method that I'm sure you've heard of is the parallax method. So the Earth rotates around the sun, and in January you see this particular star in the sky here relative to very distant stars. And 6 months later, you take the same picture of the same field, and the star will look like it's moving here. And you measure this angle here, and it's called the parallax angle, and you can convert, because you know the distance to the sun, you can very easily get the distance to the star. This is the parallax method, and you can use this to measure stars up to 5,000 light years. You don't even reach the center of the galaxy. It's very small distances. It's a very local method. This is, for instance, the method that Gaia satellites use to measure distances. And it's very important to notice here that this is a single direct distance measurement of any other distance measurement. So I'm going to show many distance methods to measure distance. All of them are based on this one first. It's one anchored in the other, which is quite interesting. You really need to trust all those assumptions if you want to trust all the distance you get from the very far distant objects. And then this is another method called this standard candles. The idea is very simple. You have a candle that you know the luminosity L, and you place it at very different distances, and the flux you receive squared. So you get the distance just by inverting this. So this can be done, for instance, with some type of stars called Cepheids. They're variable, so they're very interesting. There are stars that just go inflate and deflate, inflate and deflate. And the period of these fluctuations, it's here in days, depends on the absolute luminosity L of the star. And they are very tightly correlated. You have two types of Cepheids. So if you measure this, the period, you can measure get the luminosity of the star, and by measuring the flux, you get the distance. Okay, very basic. Another type of standard candle is supernovae. So when a star dies, it explodes, or when it reaches the mass limit, it explodes, and the explosion of the star is so bright that the brightness is comparable to the whole galaxy. It's super bright phenomenon. Then you can see this phenomenon very, very, very far distances, right? So it turns out that you can standardize the luminosity of those objects. You can try to there's an assumption that all the objects have the same luminosity, so you can measure distance with them. And because they're so bright, you can measure things of billions of light years from us. This is a very, very interesting way to do distance measurements as well. It's less famous than the others, I think. Well, not for cosmologists, but so we can measure the distance to this maser of this particular galaxy, NGC 4230. And there's some emission, some very hot gas that's spinning around the center of this galaxy. And you can measure the position of these clouds in the sky, and you can measure their velocities. So you can have a completely dynamical figure of this gas rotating, and you can derive the distance from that to the galaxy. And this is also used in cosmology. It's a very interesting measurement to use for cosmology. So this slide, I had to make it because this is recent history. I couldn't copy from a previous talk. I had to make this slide new because this is a new way to measure distances. Oh, it's a shame I cannot see very well here, but have you heard of the gravitational detections, gravitational wave detection? The first detection was amazing, right? You can see the sound of a merger of two black holes merging, and two detectors detected it, the same shape, etc. And the nice thing about this signal is that the signal, only the shape of the signal depends on the mass of the two black holes. And once you get that shape, the amplitude of the signal only depends on the distance to the object, right? Like the supernovae. So with this measurement, you can actually measure the distance to the object. But unfortunately, the error bars are quite huge. This is 410 megaparsecs, plus or minus 180. It's very bad measurement, right? But it's not a redshift measurement. It's a distance measurement to that source. And this was in 2015. It's already 4 years ago. Can you believe that? And also there was this one, which is also was amazing. The gravitational wave detection with an electromagnetic counterpart. So they actually pointed the telescopes and they saw something bright happening there. I don't know if you can see here the difference between these two images. There's a zoom in here where you have the new star appearing. That was a merger of two neutron stars, and they do emit light when they merge. It's not like the black holes. We think they don't emit light, but the two neutron stars, they emit a lot of light, and they appear like a new star instead. So you have a distance to that object here, and you can look at the paper to know more about this. So most of my lectures will be about standard rulers. What if you use standard rulers instead of standard candles? What if you have some object that you know the size in the sky, a particular size, which is the same at several different redshifts, and you can measure this and measure distance from it. And there's one, and it's called BAO, the BAO acoustic scale. I'm gonna use those terms a lot. They give us a standard ruler in the sky. So that's the idea. You can measure it across the sky, and you see an angle in the sky. And you know the size of this ruler. It turns out this ruler is 150 megaparsecs large. It's huge, it's massive, it's much larger than any galaxy cluster. And you can measure it in the sky using a telescope, but you can also measure it in the radial direction. You can measure this ruler not only across the sky, but in the radial direction, like this, as a difference in redshift. And from that, from simple geometry, again, you can measure dA here, which is the angular diameter distance, for those that know it. You can write it as a function of the h of z, as the expansion rate. I'll come back to that in a minute. And with this delta z and RD, the VAO scale, you can measure dH. dH is related to the Hubble expansion rate again. So from this slide, you can see that from VAO, you can measure h of z. That's the idea. And it turns out this measurement is very precise. They give us like a few percent or even sub-percent measurements on the distance and expansion rates from this technique. So, any questions until now? So this was all very introductory. Yes?
So you say that we have this ruler and we have this thing that is oscillating. What is that thing that was oscillating?
I'm sorry, what? Which one?
The thing that we're measuring the oscillation from?
Cepheids, the stars?
Cepheids.
Yes.
Oh.
Yes. We can measure very local things, and Cepheids, they're very bright stars, and you measure them in some other galaxies around us, but not that many. And yeah, there are stars. This ruler here, I will explain later what it is, but it's much bigger. It's cosmological scales. Like our own galaxy is 10% of a megaparsec, right? The size, and then the ruler has 150 megaparsecs. So to give an idea of the scales. So the expansion of the universe. Okay, just one word on velocities. I think you all know the Doppler effect, and galaxies that have some emission lines or absorption lines. If they go away from you, some speed, you have some redshift, and if you go towards you have blue shift. And so then you can measure velocities relating the lambda you observe with the lambda in rest frame. This gives you V. Okay, Hubble in 1929 thought, oh, let's measure Cepheids in some galaxies very close by and measure the speed of those galaxies. So, and then he did this plot, which is very ugly plot. The units were wrong, and everything. And anyway, we have those points here. He plotted the distance of those Cepheids and the velocity of those galaxies, and he found that for megaparsec scales, you see this kind of linear trend. And then he was amazed by that, and it turns out that he discovered the expansion of the universe. Right? So he created the Hubble's law, where V is proportional to D, and the proportionality, the constant is H naught. This constant is H naught. It's the Hubble constant, the famous Hubble constant, and he measures something about like 500 kilometers per second per megaparsec, which was very, very wrong, very different than it is today. And the interpretation is this one, where you have galaxies in all directions, in an expanding universe that are receding from each other, and then it explains this. So the expansion was kind of like a mystery. At the time, people were puzzled by this. And Einstein, when he created general relativity, this is the equation of GR. You have space-time here, and you have the contents of the universe in energy, the energetic contents of the universe, and GR is well matter, bent, space-time, etc. And Einstein thought that the universe was static. The universe was static, so he didn't think that the galaxies could expand. It doesn't make much sense. He thought it was static, so he created something. He added this term such that the equations of motions of the galaxy in the universe were static. So, and this constant is the famous cosmological constant. And because he wanted the universe to be static. Today, this cosmological constant, people try to find physical meaning to this constant. Some people call it anti-gravity. Some people try to associate it to vacuum energy, but still we don't know what it is. Well, Edwin Hubble showed that the universe is actually expanding. It's not static. And then Einstein was feeling very bad, and he said, "Oh no, the cosmological constant is the biggest mistake of my life." He actually said that somebody. 70 years later, you have this team of people led by these three guys that use supernova of type 1A to measure distances as a function of redshift here on the y-axis. He goes up to quite high redshifts of 1, and you have about 70 supernova here in this plot. And this is a magnitude, some distance modulus related to the brightness of those supernovae. Here you have fainter, and this is brighter. And you compare this to a model. The dashed line here in the middle is the line where the universe is just expanding, as Hubble thought, but contracting, let's say. Well, you expect a universe that is expanding to stop, right? The expansion should decelerate because galaxies are attracting each other. So you expect at least the expansion to slow down, okay? And this line here, which agrees the most with this data, is for a model where lambda, the cosmological constant, or omega lambda, if you want, is different than 0. Those two lines is for a universe with no cosmological constant, and this line is a universe with cosmological constants. And then they found for the first time that actually the universe, to explain those faint supernova, that the universe is not only expanding, but also the expansion is accelerating with time. So they actually need the cosmological constant again. And here's a plot that shows the fit of that data in 2 parameters. It's a 2-dimensional likelihood profile as a function of omega m, which is the density of matter, and this is the density of cosmological constant. And the data is preferring this. You have 1 sigma, 2 sigma, and 3 sigma contours, and the data is showing that this cosmological constant is above 0 with 3 sigma significance. So you have other lines. I don't know if you can see them. You have some very faint lines showing this division here. This line showing this side of the plot is an accelerating universe. This side of the plot is decelerating universe. You have other interesting lines here. This is the flat universe line, where omega total is equal to 1. You don't have a curvature. Universe here is closed, and universe here is open. And you're gonna see this plot again. Just spoiler alert. And I'm gonna show this because this is the big deal here. You're trying to do in cosmology is to understand this. What's going on? What is this? What is the physics of it? And also, a lot of this is dark matter, which we don't know either. But I won't talk much about dark matter. These guys got the Nobel Prize in 2011 for this first evidence of dark energy. And then Einstein is happy again because the cosmological constant is back. He was actually right again. Not only he predicted the gravitational waves, he was right about the cosmological constant. So the quest after this, of course, the quest for dark energy started, and everyone is trying to measure it. So I'm going to explain a bit how do you observe the expansion again. H of z, d of z distances, and etc. I'm going to show some equations. So if you write the expansion rate h of t as the derivative of scale factor, and the scale factor gives the scale of the universe basically. So Big Bang, this is 0, and today a is equal to 1. And because the universe is expanding, a of t is increasing, and a dot is the speed of the expansion. So basically, this is giving you the speed of the expansion. Okay. If you change t to redshift, right? Because we love redshift more than time. You can write this as a function of you can put it on Einstein equations, and you get that the the evolution of this H depends on, well, you set the initial conditions today. This is a Hubble constant again. If you put Z redshift equals 0, you have H naught. And it depends on the dark matter and magnetic matter density. It depends on dark energy, curvature, and radiation, right? So the idea is you measure this function as a function of redshift. If you can measure H of Z at several redshifts, you can put constraints on omega matter and dark energy. And the nice part is that for cosmological constants, this f of z is constant. This term doesn't depend with time. And this one depends with time with 1 plus c to the power of 3. They have very different functional dependencies. Distances in cosmology, you need to account for the expansion of the universe when you measure distance. And so you can write it in a flat universe. The distance is an actual integral of the expansion rate up to the redshift you want to look. And there's another thing that's very nice to measure to constrain gravity. It's something called the rate of structure growth. So you measure how fast structure is growing in the universe, and this is parameterized by f of z. Is basically the speed of fluctuations, how fast the speed of fluctuations grow, and they also depend on omega matter and h of z. This same equation here. So all those three things are currently the key goal of galaxy surveys now, such as BOSS and DESI. They all want to measure those three things to constrain cosmology. So I show a plot here that you're also going to see again of h of z divided by 1 plus z, which is a dot. This is the speed of expansion as a function of redshift for three cosmological models, one with more matter, less dark energy, and one with less matter and more dark energy. And the same, going to the same h naught value here, at z equals 0 today. And so dark energy, what is it? It's something that's causing the acceleration. You can think of it as anti-gravity, right? So if you have more dark energy, the expansion starts to accelerate earlier than a universe with less dark energy, with more matter. So if you can measure this curve very well, you can constrain a curve depending on your favorite dark energy model, right? And theorists have a lot of models that have many different shapes here. The problem with those models is that I cut the redshift plot up to 3, but there's some measurements at redshift of 1000 from the CMB, and those curves have to match all the data. And it's very hard to combine CMB with large-scale structure measurements from this epoch. I'll show some constraints, current constraints. So supernova, you saw this plot from the Nobel Prize. And this is what we had from 2014. There's about 10 times more supernovae. You start to fill this diagram. And the conclusions are still the same. The dark energy is still there. This is actually the last version of the supernova compilation. This is from Pantheon. It's called Pantheon, this compilation of all those surveys. And it's a very busy plot, you don't see much. But this is the lambda CPPM model, and it's very nicely in agreement with this data. So how do they look today? So this is this is the 2014 contours compared to the 98 contours of the time, because you have so much more data. And this is 1 and 2 sigma contours, the blue ones, compared to the on same scale. Yeah, it's very ugly, but it gives you an idea of how the constraints got better now. And you're still 3 sigma above 0 here. So just to zoom in, this plot here is this one. You start to shrink the axis, and these are the constraints on supernova. And I'm gonna mention later about this line here. These are the constraints from the CMB. What about BAO? I mentioned about BAO, you can measure distances. And we actually started to fill this plot, remember, of a dot as a function of z. And there's these measurements here. These are the most up-to-date measurements, most precise measurements of the expansion using BAO. And these are the references of all these points here with the redshift. To notice, these 3 measurements and these 2 are from the BOSS survey. And this is the same thing. I'm plotting the distance over the prediction from Planck. So you're taking the ratio of the measurement divided by this curve. And this is what you get. You have some similar plots. We also have this new point. We filled this point here last year with this measurement from EBOS using quasars. And it's also in agreement with Planck.
It looks like they put it on the right hand side, not on the left hand side.
Yes, because this is not exactly. This is distance as a dV, which is a combination of h and dA, and this is just h. That's why the lamina alpha is good and not here, for instance.
Is that good?
Huh?
Yeah. Okay.
Yeah. So the tension with Planck that came from lamina alpha that you heard about, it's mostly this one. When you combine these 2 dots. The combined error bar is 2.5 sigma away from the curve. But in dV, you don't see it. So how do supernova, CMB, and BAO on the same plot, how do they compare? Again, this plot from the supernova, and then I'm going to start putting the BAO constraints here. So this is the BAO constraint. So you see that here the supernova are the green ones now. If you have BAO from galaxies and all those BAO measurements combined, you have this ellipse here, much tinier, smaller than. And the dot is the best fit model from CMB, from Planck. I'm going to explain later how you get those measurements again. And these are the constraints on growth of structures from galaxy clustering. You can also measure F at several redshifts. You don't measure necessarily F, but you can measure a combination of F and the normalization of the power spectrum, sigma 8. It's a function of redshift, and this is from an EBOS measurement here. It's a compilation of all those measurements. And so the curve, the solid curve is for lambda CDM plus GR. And it's in agreement with that curve. But if you have more data, you can start to test variations of GR. If GR is not, to make sure, to try to extensions of GR. So yeah, to summarize the current picture of the expansion of the universe, you have distances and you have growth rates. So yeah, this plot is actually showing 3 types of distances, as I just mentioned. You have DH, which is the expansion rate. You have dm, it's the angular diameter distance, and this dv, which is a combination of the 2. And all the current measurements here. Good, so I'm going to talk about baryon acoustic oscillations. Most of these points, as I said, were coming from baryon acoustic oscillations. So what is this standard ruler? Right? Again, you have this ruler that's relating, that allows us to measure distances. So what is this standard ruler? What is causing it? What is creating it? So for this, we need to go back to the history of the universe again. This is Big Bang again, time is going upwards. You have the inflation era, and you have this era where the universe was a big soup of protons, electrons, and photons. Like in the song of Big Bang Theory, the whole universe was in a hot, dense state. It's true, it's very correct, very precise song. And nearly 14 billion years ago, the expansion started. And then, okay, so you have expansion, and the universe, as it expands, it goes down, the temperature will lower, and the density goes down as well, and at some point, protons and photons and electrons stopped interacting. the universe becomes opaque. Transparent. It was opaque. It's exactly, you can think of the sun as a very good analogy. You cannot see inside the sun because the photons are scattering with the protons inside of the sun, but at some point you see some surface because the photons can escape. They don't interact much more with the electrons. It's the same thing that happens here inside out. So the density goes lower, 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 and then you have the CMB emission, which is defined by the last time that the photons scattered with protons and electrons. And those photons then travel freely until they reach us, our telescopes today. Okay, this was about redshift of thousands, and then later on you have first galaxies starting to form, and you have today. So BAO comes from this hot plasma epoch. So what happens there? And you don't have, the universe, as you know, is not homogeneous, right? You have galaxies today. These originate from very, very tiny perturbations that I showed from the CMB picture. Very small perturbations in this hot plasma. And how those propagate, those perturbations evolve with time in this area here. So if you take one perturbation plotting in this two-dimensional space, it turns out that because of this pressure on the plasma, you have sound waves propagating outwards from those initial perturbations. This is exactly like sound waves in a swimming pool. You drop a rock and you have those sound waves propagating outwards. And then when the CMB is emitted, this wave stops propagating. It freezes there at that given scale. And this is the BAO scale. This is the BAO scale that today is 150 megaparsecs. So yeah, we think that this scale is the same, basically the same one than here, but only affected by expansion of the universe. The only thing that changed this ruler is the expansion of the universe. So that's why I can use this as standard ruler. The problem here is that we don't have a single perturbation and we can measure this ring perfectly. What we have in the universe is a mix of many, many perturbations like this, and they all get mixed. So you cannot measure individual BAO scales in the sky like the ruler picture. You measure actually, you need to do a statistical measurement here. You need to average all those perturbations and you put them on top of each other, and then you see a very, very faint ring around these perturbations. I'm going to come back to that later. So again, you have the CMB here, you have this acoustic scale that's hidden in this field, in this density field, and so this sound horizon or this binary acoustic scale, due to expansion of the universe, they have galaxies forming there, and you see, you can see today the baryon acoustic oscillations in the distribution of galaxies, or generally in the large-scale structure of the universe. To illustrate even more the physics of it, so as I said, is in the statistical measurement, the tool we use to measure it is the correlation function. And the correlation function, you look at the density in a given position of the universe, and you compute what is the correlation of this density with the density at the distance r from it. Right? How these things are correlated. So I'm plugging here, this is a movie, maybe we can stop it. And you cannot see half of the lines here because of the slides. This projector is not showing them. So this is the correlation function times r squared as a function of separation, r, this r here. And the BAO peak, as I mentioned, is 150 megaparsecs. If you divide by h, if you multiply by h, it's about 100. So here you have z, it's the redshift. This is the h of the universe, and this is a correlation function of all different things in the universe. You have dark matter, neutrinos, baryons, photons, and the BAO scale is a red line here. I promise. So as the universe is, you have this sound wave propagating. You don't see, what you don't see here, you see photons and baryons they are in the same line. Okay? And they propagate outwards like a sound wave. Neutrinos are these blue lines. They only interact weakly. So the equivalent of the CMB for them was much earlier on. So they stop interacting with anything much earlier times. So they just free stream away from the initial perturbation. So you can think of there's an initial perturbation here and a sound wave propagating outwards. So as the time goes, you reach the redshift of the CMB, about 1,000. You can, I don't know if you can see here, but there's this line, which is the dark matter. Dark matter doesn't interact either, only gravitationally, right? So they don't feel the pressure from the baryons and the photons. This is caused by the pressure between baryons and photons, but dark matter doesn't feel this pressure. So the dark matter is just here. You don't see it much, but it's there. And then recombination happens, the CMB is emitted, the universe becomes transparent, a redshift of 1,000, and the photons start to be different than the baryons. The baryons just stay there, frozen in that position, and the photons free stream away, like the neutrinos did in the past. And then you have this thing growing here at the BAO scale. And as time goes, dark matter falls into the potential well of the baryons, and the baryons fall in the potential well of the dark matter. And you have this function up here with this very distinct peak, and that's the BAO peak. That a redshift 2 up to today looks like that. So if you can measure this correlation function in the data, and you can measure up to this correlation function up to very, very large scales, and if you can see the peak, then you can measure the BAO and you can measure expansion. BAO and the CMB. This is actually the first time that BAO was detected. It was actually in the CMB. Again, this map is showing those fluctuations. They are temperature fluctuations, so we can write them as delta T. You have an angle in the sky, 1, and angle 2 in the sky, and you do correlation function with that. And you can decompose this map here into spherical harmonics, like in quantum mechanics. And the coefficients ALM, you get those coefficients from this composition, and the correlation function translates into spherical harmonic space, and you get the variance of those ALMs as a function of L.
The correlations are moving across, increasing the distance in space, or difference.
So here it's in angle. So you look at what's the correlation as a function of the angle between these two vectors.
Okay. In statistics, this graph you draw the correlation. It's usually called a variogram, but you haven't assigned any kind of model to it.
No, it's just you measure. It's an estimator of the covariance, if you want. You have this is your random variable delta T, which is a function. You have several realizations of it across the sky, and you're computing the covariance as a function of distance between these two.
And you're increasing also the data you have to make it sharper. The previous graph of the correlation.
Yeah.
So what are you increasing?
So
we have something.
Yeah. Let me put in the end. If I can. So this is a model. This is a theoretical model, and it's evolving in time. What you measure in the CMB is just a fixed picture at a redshift of 1,000. So what you're measuring, anyway. So if you have like a huge volume of data of deltas, then you can compute the correlation between a delta in a given position with the delta at the separation r from it. and then you, instead of, you don't have many realizations to do the ensemble average. You just have one universe. So what you do this, you assume the universe is all the same, and you do pick many pairs of the same separation, and then you can compute the variance from that. So for the CMB, it's the same idea. You have temperature in a two-dimensional map, where every pixel in your map has a different delta, and you compute the correlations between deltas in one location to the sky and as a function of the separation between these two pixels. So we actually don't do it this way. We do it in spherical harmonic space, some sort of Fourier transform of that. But what you get is a decomposition of ALMs in terms of ALMs. You compute the variance of those ALMs as a function of L. L is the conjugate variable of theta, or the angle in the sky. So you measure this. This is the angular power spectrum. It's the variance of ALMs as a function of L. And then you can see those oscillations. I'm sure you've seen this plot before. The error bars are smaller than the width of this line. And the line is the best model for these correlations in the CMB. And those oscillations, what was a peak in real space, in this Fourier space equivalent, this peak becomes oscillations. And this is actually the name where it comes from, baryon oscillations, bar oscillations on the CMB. And then you can measure this, you can measure actually 9 oscillations, 9 acoustic peaks. And from this you can derive theta star, which is this angle in the sky, the corresponding angle in the sky of this BAO. And the CMB gives a 0.05% constraint. I'm not speaking of 5% constraint. I'm speaking of 0.05%. This is super small, super precise measurement that you can see here of the baryon acoustic oscillation scale in the sky with the CMB. It's actually the best constraint you can have from what you have today. So how do you relate this angle with cosmology? So R is this scale in megaparsecs, and dm is this distance to the CMB. Theta is an angle in the sky, right? How do you relate? So R star is this distance that the wave propagated until the CMB was emitted. So it's an integral from time equals 0 to time equals CMB of the speed of this wave, the sound speed of this wave. And the sound speed of this wave is related to this thing here, where R is omega baryons and omega rho baryons and rho photons. So how far this sound propagated, this acoustic wave propagated, depends on the density of baryons, the density of radiation, and the density of dark matter, which I'm writing as a function of omega. The CMB temperature itself gives you omega R. So basically, the sound horizon depends on omega and omega baryons. So from that, you can put constraints from the BAO measurement on the CMB. You can put constraints on omega n and omega b. If you assume the universe is flat, which is a big assumption, you get omega lambda, just doing one minus omega n. Okay, but that's a lot of constraint coming just from the BAO. But most of the information actually comes from the relative amplitude of those peaks here. Okay, so if you fit, this is the vanilla model for the CMB. It's only a 6-parameter model, which is amazing. So you can fit all those data points. Yes.
La función de correlación es una medida de la polinomial. Puedes hablar de galaxias, puedes hablar de cúmulos, puedes hablar de filamentos, depende de la escala.
Sí.
Cuando hablas de fluctuaciones bariómicas ¿De qué correlación estás hablando de escalas? Si le vi la gráfica
Sí.
de tu correlación con el eje X, que no sé qué.
Ah, muy bien. Sí, buena pregunta. Entonces, esta L lo puedes pensar como 180 grados, no, la escala angular en el cielo es 180 grados dividido por L. O sea que esto acá, bueno, sí, el cielo entero es L0. El dipolo es L2. L igual a 2. O sea, son fluctuaciones de tamaño 180 grados en el cielo, o 90 grados en el cielo. Cuando vas aumentando L, vas achicando la separación en el cielo. O sea, más pequeñas escalas. O sea, estas son escalas muy grandes en el cielo. Y esta escala, acá, situación, que es la misma, es la escala de agua. Que es más o menos medio grado, 1 grado en el cielo. Y bueno, y ahí vas a correlaciones a mucho más pequeñas escalas, separaciones mucho más pequeñas. ¿Y por qué las barras de error son mucho más chiquitas acá? Las barras son mucho más chiquitas porque tienen mucho más pares para medir esa correlación cuando las escalas son pequeñas. Solo tenés un cielo. Entonces las grandes escalas no tenés muchos. Tenés 1, 2, 3, ya está. Entonces la varianza tiene una barra de error muy grande. Entonces L es una manera de ver la escala, pero invertida. ¿Está claro?
Entonces, suavizas esas covariantes que estás estimando por la aproximada de
Ah, no lo suavizas. Eso es lo que sale del cielo. Bueno, hay una suavización natural porque el instrumento tiene una suavización. El instrumento tiene una resolución, ¿no? Por decir.
Pero no es sobre, digamos, sobre la estimación de la función de covariancia.
No.
Se me hace como chistoso que esté súper, que no esté toda brincosa.
Ruidosa.
Ajá, toda ruidosa.
Sí. No, hay correlaciones entre los puntos también. No son todos independientes. Si fueran todos independientes, bueno. No, acá se ve un poco, que son más o menos independientes. Pero hay un poco de correlación porque no está sobresalando el cielo entero, hay unos problemas estadísticos que pasan por no observar el cielo entero. Y el instrumento te agrega correlación entre los distintos L's. En cosmología, en el modelo más simple de cosmología, las informaciones entre cada distintos L's es independiente, pero bueno, ese es más de mucho detalle. Es todo tomado en cuenta. No así, no, So, any questions? ¿Otras preguntas? Sí, ese no es un plot muy fácil de explicar, entonces la voy a pasar aquí. Sí, vos sabés, ¿no? Porque otra vez explicaste.
Vamos a practicar un poquito más en la tarde mejor.
¿Cómo?
Vamos a practicar de nuevo, creo que
¿Vos vas a mostrar también?
más tarde y Gustavo mañana también.
Sí. Perfecto.
Escuchar 3 o 4 veces.
So, stay tuned.
Preparen sus preguntas.
Sí, es difícil, entonces van a explicar muchas veces. Muy bien. Ok, bueno, la idea es, so the amazing part is that this model I say, the soup, hot soup, Big Bang expansion, you put this with only 6 parameters, you can fit all those scales from some super horizon scales. So scales that are much bigger than anything that was ever in connection gravitationally. And very small scales, quite small scales. And you can fit that with six parameters. And you can get very tiny constraints. If you look at those error bars, and put the square here, this is omega variance, this is omega cold dark matter, and you see how tiny those errors are. And this is the theta MC, it's related to the baryon-Bosch scale. Again, from these 6 parameters, you can derive parameters, such as the age of the universe, here, 13.8 billion years, plus or minus 0. So we know in this model the age of the universe very precisely. Another interesting derived parameter is H naught. H naught is a derived parameter. This is very important to keep in mind that the CMB does not measure H naught. It's a prediction. H naught is the expansion of the universe today, and the CMB is measuring stuff at reaching 1,000. Okay, so you don't measure H naught from the CMB. It's a derived parameter, and it's 67.35%. Okay, when we talk about tensions with local measurements, yeah, you need to take this into account. H naught is a derived parameter from the cosmological model from very, very far distances, and the other measurements are local. And then you have other parameters here. And you have also the acoustic scale in comoving megaparsecs, in 150 megaparsecs. This is the BAO size, the BAO ruler. So remember the dark energy, dark matter plot? Planck is such a precise measurement that the axis is tiny here. You don't even see 0 and 1. And these are the constraints you get from Planck. And the dashed line is the flat universe line. So for Planck season and the universe are very close to flat universe. And then you can remember the constraints on supernova, right? They were like this. I'm actually showing them here in this direction, and BAO as well in this direction. So when you combine all these, like BAO here, you have this tiny ellipse here on the constraint on the cosmological model. Okay, I still have 20 minutes, right? Or more. No, 1:30. Huh? No, it's 1:30.
It's 1:30.
Yeah.
Yeah.
I'm so sorry about it. It's very hot. And hungry. No, I'm gonna finish before. No worries. It's okay. BAO in the large scale structure. So I talked about CMB. Now I'm gonna talk about large scale structure. Again, I'm showing this picture here. I mentioned also, I talked about this measurement here of BAO here. Now I'm going to talk about measuring BAO here. So again, correlations. You need to find overdensities in the universe. You define those deltas. I should have written. Well, for the large scale structure of the universe, I didn't write the equation there, but you assume that the universe. Where is it? It's okay. So let's say your universe is 1D. So you have a position x, and here in the y-axis you have rho, the density of the universe is there. So you have some mean value of rho, and then you have, because of fluctuations, you have things like this, and you have spikes. It fluctuates around the average, right? And then you have spikes, etc. Okay, this is the density field as you see, and this is 0. So you have voids, you have spikes where the galaxies form, and this is the quantity you're interested in to look into correlations on. So what you do, you define deltas x as just the fluctuations around the mean of this thing. So you do rho x minus rho average divided by rho average. So, but how do you compute the density of the universe in a given location? If you look at the sky, you see some galaxies here and there. Yeah, so you can see, for instance, something like this, right? Or how to get the density at a given position. So one thing you can do is actually count galaxies. So you look at the galaxies and you count you put them in cells. You say, oh, how many galaxies I have here compared to this cell, and you can compute this delta in a box. So the problem is the galaxies trace very dense regions. So this is a figure showing a simulation, n-body simulation with gas. And So you have those blobs of more dense matter here, and the galaxies, they will only form in these very high density regions of the universe. So you don't have galaxies here, for instance, where there's nothing. So it's very hard to measure those deltas when you don't have any galaxies, right? So it's kind of misleading. You're not actually measuring the density of the matter, the total matter. You do have dark matter there. You have matter, you have baryons, but the galaxies, they're not showing it to you, and so on. So this is one way, actually. You can use galaxies to measure deltas. You can still use them to measure BAO. And the other way, which is the topic of this series of lectures, is the laminar forest. The laminar forest, I'll talk about it in the next lecture. But you can measure the density in all those regions here, basically, where the dashed lines. You can measure the density like a tomography. You measure the density in all those locations here. In every single point of this line, you can measure the density. And then you can do correlations from that. It's very different than the galaxies. So I'll talk about more about the galaxies, how to measure BAO on the galaxies. This is a sketch of what a galaxy survey looks like. You pick a telescope, you measure many millions of galaxies in the sky, you measure all the redshifts of them, and then you make a map of this as a function of RA, DAC, and redshift. And then you count pairs, and this correlation will be basically what's the average number of pairs at a given separation as a function of separation. And you compare that to a random distribution of points. So you're going to see that this, because of BAO, you can see a slightly over rings. This is illustration purposes. This is what happens really. It's very exaggerated. So you have central density, and you have this BAO peak, and you have galaxies around it. So what you see when you have a galaxy survey is you count pairs, and then you have slightly more pairs at the BAO scale than smaller scales and large scale. So if you compute the correlation function using galaxies, this is what it looks like. And this is actually a measurement from 2012. And you can see how amazing, you can see the peak, the BAO peak here, at a scale that's very roughly the BAO scale, 150 megaparsecs. And from this data, you fit a model and you estimate the position of this peak. So how far from zero this peak is. And that's the BAO measurement from a galaxy survey. Again, remember that BAO in a galaxy survey, you can measure it in an angle in the sky, but you can also measure it in a radial direction. It's actually the correlation function is a function of separation, but also what direction of the separation. So we can apply it as a function of radial separations and transverse separations. Same correlation function that I showed before. This is like a model, and you can see the BAO peak here appearing. Okay, you can measure. So you can measure actually correlation function. You don't need to average all those directions. You can measure it in what's called wedges. You do averages of the correlation in angles like this. And what you have is something that looks like this. So the correlation function, the blue one is the most radial correlation function. And that gives you this peak. And the transverse one is this one, gives you these points. And they are different because of redshift space distortions, or something called redshift space distortions. The fact that you're measuring redshifts breaks the symmetry of this. The redshift, they have peculiar motions, and those peculiar motions, they're correlated with the density, etc. So you have an enhancement of a different power, different amplitude of the correlations in the radial direction of that. And what's interesting about this is that you can try to measure independently the BAO scale in the transverse direction than in the radial direction. And they give you different information, different amount of information. The BAO in transverse direction here gives you, remember, an angle in the sky, gives you dA. And a radial measurement of BAO gives you the H of Z. Right? This is the constraints of the measurement. This is from 2017. The measurements of so you measure the correlation function, and you fit this fit BAO, and you translate them into H of Z and dA, which is similar to this one. And these are the measurements, which one of them, Mariana, was the main author. And this is from BAO, from galaxies, at a redshift of 0.4 to 0.6. And this is the Planck. Remember the very thin constraints from Planck? This is the Planck prediction. What Planck predicts there. It's super tiny. But they're in agreement. That is also shown here in this plot that I've shown already. Those 3 points, they're in agreement with the Planck prediction. And this is a very bad picture of the correlation function, the BAO peak of those 3 points from the latest BOSS measurement here. And these 2 points here are coming from a different way of measuring the correlation function, not with galaxies, it's with the Lamanov forest. So Lamanov forest give you a measurement of BAO a much higher redshift with a very, very, very different way of measuring it. And those are the papers, the 2 papers from the final papers from BOSS. Actually, this is not the last one. And there's some new ones from like a month ago from the eBOSS survey. They have more data and they have a new measurement of these 2 points here. Okay, I think this is the end of the first lecture. Any questions for now on the BAO part? Preguntas en español. We have 40 minutes. Okay, it's okay. So, yes. Sí. Sí.
La gráfica, o sea, el centro es el punto de observación, porque es la correlación.
Es, mira, voy a estar acá. Vos estás acá y vos vas a mirar el cielo a una distancia, no sé, 2000 megaparsecs, 3000 megaparsecs, y estás mirando separaciones, esa correlación, y X está acá y R es un vector como este, y vos contás cuál es el número de pares a esta distancia. Pero se puede medir esta distancia así, o así, o así. Estas separaciones son separaciones radiales, ¿no? Una galaxia está más lejos, y estas son separaciones angulares. Y a cero, cuando vas achicando el tamaño de la separación, vas a centrar a cero. Y ahí el cero es el pico de las fluctuaciones primordiales de la animación que sufre. Entonces, esta es la correlación mucho más fuerte acá. Acá ves la correlación entre las galaxias que están en el mismo halo, y estas son correlaciones mucho más grandes escalas, donde la gravedad no actuó mucho, la gravedad U, y que son de 100 megaparsecs, o range. ¿Entendés?
¿Puedo comentar algo?
¿Ah?
Si vas a estar en los proyectos de 3 Point, vas a aprender a hacer eso. El comercial.
Spoiler alert. Spoiler. La función de 3 puntos es lo mismo que, ¿no? Pero al lugar de delta, delta, tenés delta, delta, delta. Y tenés triángulos. Tenés uno y un triángulo, y metís correlaciones en triángulos. Y eso es mucho más complicado porque no solamente tenés la orientación del primer vector, pero también del segundo, ¿no? Y tener todas las combinaciones posibles, es mucho más complicado, pero Sebastián, Ricardo. Muy bien.
No, Está dividido, también está.
¿Sí?
Sí.
Es un truco acá, porque esta información está multiplicada 4 veces. O se puede pensar en un par de galaxias acá, si me dice un par de galaxias así, es lo mismo que un par de galaxias así, ¿no? Entonces, la información de verdad está acá. Esto es una copia de esta información. Todas las galaxias son las mismas, entonces un par así tiene la misma información. Por eso yo puse los wedges acá nomás. Y esto es un función, no lo dije, pero es una función de redshift también, ¿no? Entre 0,2 y 0,5, 0,4, 0,6, 0,5, 0,7. Y por eso puedes medir esos 3 puntos. 3 medidas. Muy bien. ¿Otra pregunta? ¿Puedes terminar? Bueno, sí. So, I started saying that distances are not easy. I hope I convinced you. Distances are not easy in astronomy. There's many other methods I didn't mention, but they are all indirect. They rely on correlations between different stuff, and they're all based, to start with the parallax. The universe is expanding. The universe's expansion is accelerating, and we don't know why. We still don't know. Although we found a cool name for it. Very cool name. Dark energy. It's like American advertisement. Done right. Dark energy. So cool. But we don't know what it is. And variable oscillations give us a very powerful ruler, a powerful way to measure distances, as I showed you. Those error bars are very tiny, and few percent level. The video can be seen in the CMB very precisely, which is very hard to break. If you want to try a different model to fit that data, it's very hard because those error bars are super small. And the current model is working so well that it's very hard to change this model. But in the large scale structures, you can also see video. You can see the expansion rate of video. And you see that this is very far from being definitive, right? We don't know if this is the actual correct model. It fits the data, most of it, but we don't know if it's the actual truth, right? We will never know, really. If we have more measurements to super tiny error bars, maybe we can see if lambda CDM is still valid or not. We can probably try to break lambda CDM by doing more measurements here. So, in the future lectures, I'm going to talk about measuring this kind of things. The future survey called DESI, they plan to measure this with very, very hard, 10 times better error bars across many redshifts up to 3.5. And just to give you a spoiler for what I'm going to talk about for DESI. And then, so yeah, I hope I convinced you that BAO, this diagram, putting the BAO measurements on this diagram and trying to constrain dark energy is very powerful. I think this is at least the near future for dark energy is to measure BAO and put them on that plot and try to fit your best model and try to see if lambda CDM works. So, yes, and then in parallel, theorists try to put theories to explain dark energy in a more fundamental way than just, it's a cosmological constant. Maybe it's a fluid, maybe it's a scalar field, maybe is inflation happening again? So yeah. So I'll stop here.
Más preguntas, tenemos mucho tiempo.
That's really true that the effect over in the log space is.
Yes. Yes. It's true. I have a friend that was very bored with the exercise of putting the Eiffel Tower in the log space. You can probably Google that. I don't know. Any more relevant questions?
I have one a bit tricky one. So do you have an explanation for the reason why we have really different results between the DV and the H over the C? Why we can remove what the extra information, the difference in the information we get for the two measurements to have an agreement or a pretty.
Yeah. So it's tricky. So let's go back to this plot here. So do you understand? dA comes from this, H comes from this, and dV actually comes from the average, if you do one average of this. So the first plot I showed from Box is the monopole. It's called the monopole of the correlation function. Where is it? This one. That's showing exactly that. It's not wedges, but you do the average across the whole thing. So when you measure the DAOP, you're mixing dA and H. You're actually mixing 2 times dA, because you have 2 dimensions, angular dimensions, and 1 time H. So dV, it's actually, dV, you can write it as proportional to dA squared over times dH, where dH is simply C over H of Z. So there's now actual more information. This is actually mixing the two. So you can actually extract the dV constraint just from this plot. This is H, right, on the y-axis, and dN or dA on the x-axis, and dV is just giving you a direction of the best, which I think is something like this. Just giving you the best constraint from a galaxy survey. Does that make sense?
Yeah. I was trying to figure out if we had like an idea with the hands that why we can have in one space a real difference of 2.5 sigma difference. And the other one that appears to be in very good agreement. So I don't know if you just finally propagated the errors because we have one more.
Yeah, if you have, for instance, if this is the dV direction you are measuring here, but your plane is here.
So, yeah.
You have a tension in 2D plane, but in 1D you will see it.
Okay, I understand. It's a marginalization.
Yes.
Okay.
Yes. The other thing, actually, I didn't mention is that for dV, you just assume that all the distances scale with one scale, one alpha, that you get your, that all the radial and transverse distances scale with the same thing. Well, here you don't assume that. You assume that maybe radial distances, and you have the Alcock-Paczynski. I didn't mention that. You have a Alcock-Paczynski effect, and so this is measuring that too. There was a question there?
Sí. Teniendo en cuenta, la función de correlación es una expresión de la distancia a una potencia, una cierta potencia. En ese sentido es estadístico, claro, es que estar midiendo distancias, ver el acumulamiento de galaxias. ¿En qué sentido esto restringe la energía?
Bueno, la correlación te da esto, ¿no? Las correlaciones te dan los puntos acá. Le dedicas correlación y te da estos puntos con la barra de error, que son una función de la distancia. Entonces medí la correlación y la correlación cae con la distancia. Pero en la escala de AU tenés ese pico que aparece, es un exceso de correlación que aparece. Y ese pico de AU lo transformas en una medida de la expansión del universo. Y la expansión del universo, si pones esa medida, si la transformas y la pones en este plot, si tienes más o menos energía oscura, esta línea sube o baja. Entonces, si medís ese pico de AU con un survey a un redshift, vas a poner un punto acá, en este plot. Y esto te va a dar una constraint, ¿no? Una medida de ¿cuánto de energía oscura tenés en tu universo?
Creo que las transparencias que puso al principio explican un poco eso. Lo que se tiene, digamos, de este BAO se espera que sea una esfera, entonces uno puede sacar un radio medio, y ese radio, esa distancia, conforme el universo crece, va a crecer también debido a la expansión del universo. Entonces, tú tienes una burbuja a una distancia muy lejana, y luego tienes burbujas más cercanas y más, y mides el radio a diferentes corrimientos al rojo, diferentes burbujas que no están conectadas entre sí. Y la energía oscura es la predominante diferencia en cómo crece el tamaño de estas esferas que lo asocias al crecimiento del universo. Y de ahí sacas información sobre la evolución del universo, por lo tanto, la energía oscura. Entonces, no nada más es en una sola esfera, sino tener muchas esferas que te permiten poner todos esos puntos, diferentes expansiones, diferentes energías oscuras o modelos de energía oscura, que ponen puntos en forma de lugares diferentes.
¿Por qué hay mayor correlación en la dirección radial que en la transversal?
Eso por cuando me dicen un redshift, tenés dos cosas, ¿no? Que te hace redshift. Es una velocidad, ¿no? Tienes la velocidad de la expansión del universo, ¿no? Galaxias que están más lejos, más lejanas, tienen un más alto redshift por la expansión. Y otra componente del redshift es la velocidad particular, se llama partícula peculiar, no sé, de la galaxia que se está moviendo ahí en su vecindad local, por la gravedad, no está parada, no está estática, se está moviendo, está siendo atraída por otra galaxia. Entonces, el redshift es una combinación de los dos. Entonces, ¿qué pasa? Cuando medís la correlación, la función de correlación, estás transformando estos redshifts en distancias, básicamente, y cuando haces eso, no estás calculando la verdadera distancia, es una distancia que está mal, porque una parte del redshift no es cosmológico, una parte es velocidad. Entonces eso te hace una distorsión de la correlación, te crea una correlación que está distorcida un poco. Y eso es lo que ves ahí, en este plot. Sí, bueno, no es intuitivo, la velocidad y chao, punto. Sí, si escribís el modelo más simple de redshift space distortions, en promedio las galaxias se atraen por gravedad, una cae sobre la otra, en promedio. Y solamente de suponer eso te hace esta distorsión así, de ese tipo. Te causa una amplitud más fuerte en la dirección radial. Pero ahí está bien esto, los colores. Sí, es en power spectrum. Sí. Entonces tenés es una distorsión. Ahora no me acuerdo si está bien los colores, yo creo que sí. Pero en power spectrum tenés más power en la dirección radial. Pero esta es la correlación, entonces esta es una transformada de Fourier entre los dos. Pero esa es la idea. El redshift es eso. Y eso, de hecho, se puede usar para medir F, el growth rate. Eso es lo que se usa. La gente no solamente usa esta información para medir la posición del pico, pero esta diferencia de amplitud te da una idea de las velocidades de galaxias, ¿no? Y esas velocidades se pueden calcular en un modelo con GR, con relatividad general. Haces una predicción de cuáles son las velocidades de esas galaxias. Y eso te da una amplitud. Pero si cambias tu modelo o tu modelo de gravedad, te puede dar otra cosa. Entonces, se llama RST, un idioma de survey. Estoy haciendo RST, estoy midiendo esta diferencia de amplitud y tratando de sacar el valor de F que está en el plot que está. A ver, ¿dónde está?
Yo tengo uno, si quieres.
Te da este F, esa medida. Entonces, por un lado te hace esa distorsión de la correlación, por otro lado te da mucha información sobre la gravedad.
Yo, ¿qué piensas de todos estos modelos que extienden lambdas y diem, así con cosas muy raras inspirados en la tensión de Lyman alfa?
¿Puedo abrir otro slide acá?
Sí.
Rápido. Yo hice una charla parecida.
Porque es algo que causa mucha entusiasmo.
Sí, sí y no. Mira,
Good. Good to know.
La respuesta, bueno, ¿qué se puede hacer con modelos de gravedad? ¿No? Bueno, acá hay una lista de modelos de gravedad que la gente lo pone como extensión a lambda CDM plus GR. ¿No? Este está en el paper, es muy interesante. Es corto y se puede leer. Ellos combinan todos los observables, supernova, BAO, RST, CMB, y hacen fits de estos modelos. Todos esos modelos. Y acá te da la lista de los parámetros que agregan al modelo. Y bueno, tenés las referencias para cada modelo. Bueno, entonces el primero es flat lambda CDM. El segundo no flat lambda CDM, que todos conocemos. Y después es un carnaval de modelos. Y acá están los constraints. Ellos hacen fits de todos los datos juntos, combinados. Y esto es chi-square de los modelos y probability. ¿No? Y ves que todos los modelos casi están acá, con más o menos el mismo chi-square, ¿no? Y más o menos la misma probabilidad. Y esto acá es un zoom en esta región. Y están todos más o menos en el mismo lugar. No hay uno que sale. ¿Por qué? Porque el lambda CDM, que es el más simple de todos, ya fitea muy bien los datos. ¿Entendés? Entonces, si agregas parámetros en tu modelo, más free parámetros, bueno, fiteas los datos también. El chi-square es el mismo, no cambia. Y la probabilidad sube o baja, pero depende de cuántos parámetros tenés. Entonces, por ahora,
pero CMB es el CMB completo de plan.
Sí.
¿O solamente distancias?
No, es el CMB, el Temperature per Spectrum, todo, creo que sí. Sí, cuando digo CMB no es solo que hago todo.
Entonces el chi-square no puede ser 160.
Yo no creo que fite, sí, no creo que fite el Power Spectrum.
Porque hay modelos ahí que tienen perturbaciones. Y cuando ya consideras perturbaciones, sí hay una diferencia.
Sí.
Sí, bueno,
es verdad.
los multipolos del CMB son cientos.
Sí, miles.
Y las supernovas también, ahora ya son bien.
Sí, entonces hay que mirar qué quiere decir ese texto. No sé muy bien.
Porque sí se me hace raro, por ejemplo, este es ED, creo que es Early Dark Energy. Entonces sí afecta la perturbación del CMB. Y por lo tanto sí debería de, ya sea muy malo o regularmente malo.
Sí, no, es verdad. Sí, hay que ver cómo él define el chi-square. No sé cuál es la descripción, hay que mirar el paper. Pero la idea es la misma, que el chi-square no cambie mucho, un poquito, ¿no? Todo está para todos los modelos. Y entonces la conclusión es que no se sabe lo que es Dark Energy todavía. Y uno necesita más datos para tratar de aumentar la diferencia entre estos tipos, ¿no? Hay algunos que este está muerto, tampoco lejos, pero los otros están ahí.
Yo quisiera agregar un comentario, digamos. Hay dos instituciones que son muy parecidas, muy diferentes. Uno es cuál es el mejor modelo que ajusta los datos y demás, donde el número de parámetros es muy importante en la consideración y ahí probablemente lambda es uno de los mejores modelos, si no el mejor. Y la otra pregunta es cuál es la dinámica realmente del universo. ¿Qué entendemos del universo ahí donde no te importa necesariamente qué parámetros son? Tal vez no tienes la teoría final todavía, tal vez tengas una teoría que va a venir después, pero si no te preguntas cuál es la dinámica, independientemente de cuál es el mejor modelo, nunca averiguas cuál es el mejor ajuste a los datos, nada más de las observaciones independientemente del modelo. Y entonces, creo que hay un énfasis últimamente en nada más hablar del mejor modelo y la comunidad se está quedando demasiado en la molecular matter en general, precisamente por el número bajo de parámetros libres que tiene, pero no necesariamente porque es el mejor ajuste a las observaciones que se tienen. Y hay que estar abierto, digamos, a ambas posibilidades.
No, estoy de acuerdo. Total.
Sí, lo llamo.
No agradezcamos a
Antes de que se vayan, tenemos dos cosas. Mariana tiene un anuncio que hacer. Ok, bueno, mientras Mariana instala, lo otro, para las personas que están